Blume on few body physics of emitter couple back. Please, Dr.
Yeah, thank you very much, Tobias. And again, thank you for having me at this school. And thanks to everybody who's sticking around.
You are muted. You are muted, Dr. There is no sound. I see that your microphone is on.
No, we can hear her.
But
Can you not hear me?
oh, sorry. You are okay. I forgot it.
Okay, so you can actually.
Everything is fine. Yeah.
Oh, okay.
Yeah, please, Doctor.
Okay, you can probably also see my airport sign, which I don't actually know how to get rid of. So
okay. No, that is a cross. Just click on the cross. Yeah.
Yeah, it does not work. Okay, let me try something.
Maybe you close and open again.
So this works. Great, thank you so much. So everybody can hear me okay? Yeah, okay, great. So yeah, thank you for having me. And so since this is the last lecture on this in the school, I thought what I do is I try to sort of expand the theme of universality to a slightly different topic. And in particular, what I want to look at is sort of a discrete system. And in my case, this is a bath. And I want to couple emitters to this bath. And it is a little bit different, but hopefully you will see how universality arises in this context as well. And actually, at least in one slide or half a slide, I will address one of the comments that you saw in the chat earlier on. I think it was yesterday or maybe on Tuesday, where somebody asked whether there's actually an Efimov effect in the context of condensed matter physics. And I will address this and refer to a paper in that area. So let me just sort of put this a little bit into context, because as I mentioned, it's a little bit different from the sort of talks and presentations, the topics you've heard about previously. So on Monday, I talked about tunneling dynamics. So in that case, the interactions were really fully characterized by the S-wave scattering lengths and then the 1 decoupling constant. But it was important to really sort of fine-tune the trap parameters. And so in that sense, the trap shape was non-universal. And then on Tuesday, I talked about the helium dimer. Again, I talked about dynamics. So today, I'm also going to talk about dynamics. And in the case of the helium dimer, we looked at dissociative dynamics. In this case, the initial state was really essentially fully universal, but the laser molecule interaction sort of grabbed on in the non-universal regime. So there was sort of an interplay between universal and non-universal physics. And then yesterday, I talked about spin-orbit coupling. This is the only talk where I focused just on static properties. And there we looked at the Efimov scenario and asked what happens to the Efimov scenario if we change the single particle dispersion. And I showed you that there's this generalized radial scaling law that's emerging. So today, I'm also going to talk about a modified single particle dispersion. And that arises due to the fact that the baths that I'm considering is actually kind of like a lattice structure. So we will have a modified single particle dispersion, but I'm gonna look at the end of my talk at the dynamics. And just as I sort of in the first two lectures where I discussed dynamics, to understand the dynamics, it's always useful to first look at the static properties of the system. And I will follow that scheme today as well. So let me just sort of outline very roughly what's the idea that we are looking at. So what I want to look at is I want to look at an emitter or multiple emitters that are coupled to a cavity array. And I'm going to discuss a little bit more what I actually mean by this. But for now, you can really think about this as some sort of discrete system. So we have this two-level system, you know, just say an atom with two levels. Typically, we call this ground and excited state. And somehow this state is, the system is initialized in the excited state here. And then it's also coupled to a bath. So let me just sort of indicate my bath very wiggly here as this red line. And there's some sort of coupling between our two-level emitter and this bath. And what we're going to ask is, what is the probability of the emitter or later on emitters to stay in the excited state? And then the other thing that I'd already pointed out earlier in sort of the introductory comments, actually, this bath is not just sort of some wiggly line, but it's actually a cavity array. So it's some sort of discrete system where we have individual sites where whatever we have in the bath, and I'll be talking about photons, where the photons can sort of hop from here to here to here to here. And that is sort of the question that I want to address. And of course, the question that is, what is that population of the emitter to be in the excited state? That depends on a number of things. One, it depends on how the emitter is coupled to the cavity array. So it really depends on how this red line that I drew here, this coupling, how this is realized. And of course, it also depends on the characteristics of this cavity array. So the way I've drawn it here is it's just sort of a one-dimensional chain, but it could be two-dimensional, or it could be three-dimensional, and so on. Okay, so the other thing that I want to sort of emphasize here is that what we're interested in is the universal regime, or we're sort of interested in looking at universal physics. And so in my context here, what this means is that I want to look at a regime where this bath that I haven't sort of quantified very much yet, where this bath supports a universal two-body bound state. And universal in this context means supports a bound state, a two-body bound state that depends on just very few parameters and sort of is large in some context, right? Previously, when we talked about the universal window, typically we are working in the large scattering length regime. And so we will have to think about what universal or what a large bound state is in the context of this array. So this is sort of what we want to look at, and hopefully I can walk you through this today. Before I go through the details, let me sort of step back a little bit and just a bit more broadly motivate why we're actually interested in this. So here I have the bath, and I have this coupling between our system and the bath. So in my previous discussion, the system was my two-level emitter that has a ground state and an excited state. And I said what we're going to look at here is some sort of array of that I want to specify a little bit more. And so there's really sort of different ways of thinking about it. One way I can think about the system is I can say, well, let me think about this here as a probe. and sort of let me sort of ask, how much information can I get about my environment by not just having one probe, but by having two level emitters sitting here? And you know, if I have two probes, so sort of two emitters that are sort of coupled to this path, how much more can I learn from the system or about the system compared to when I only have one emitter? And in particular, you know, if I now sort of maybe put the two emitters here in an entangled state, can I take advantage of some sort of quantum mechanical effects? So this is sort of one of the questions that, you know, very broadly motivate us. Going sort of a little bit further, I can also think about this as sort of in a different way. I can say, right, this here, my two level emitter, maybe, you know, maybe I'm not so much interested in using this as a probe, but maybe what I can do is I can say, right, I want to manipulate the probability of the emitter to be in the excited state. So I want to manipulate how much radiation is coming off of the emitter. And maybe the way I can do this is by actually modifying my baths. And that's sort of one viewpoint that we're going to take throughout this talk. Namely, if we have a non-trivial mode structure of our baths, in particular, if we do have this two-body bound state that's supported by environment, by our bath, can we, by sort of maybe talking or maybe, you know, sort of coupling this emitter somehow to this two-body bound state, can we actually then manipulate how the emitter is losing its population or going from the excited state to the ground state? This is sort of the broader motivation of this topic. And, you know, quite generally, why are we interested in this? In nature, we always have a system, but we never have a system in isolation. So there's also the environment, and the environment might be perturbing how our system is behaving. And maybe if we design our environment in a particular way, then we can actually manipulate our system. So quite generally, we can ask the question whether sort of environmental noise could be turned around, and can we actually use this to our advantage to sort of make our system behave in a way that's more advantageous than it would be without this environment being there. So essentially, usually we think about environment as noise, and that's bad, but alternatively, you could sort of say, well, maybe given that the environment is there, that we do have dissipation and this disturbance in general, maybe we can actually take that to our advantage and then influence what's happening to the system itself. So that would be a very, very broad motivation for sort of this type of work that I'm going to discuss. Okay, so with this, let me discuss a little bit more specifically what I have in mind. And to start with, I'm going to discuss the array that we're looking at. So to start with, I'm not going to look at the emitter. I'm going to postpone that discussion for a while, and I'm just going to characterize the bath that we are using. And as I mentioned, what we want to look at is we want to sort of work in a regime, you know, because I'm a few-body physicist and I do like universality. We want to look at a regime where this bath supports a two-body bound state. And okay, how do we get this? Well, we can get this by looking at this type of a Hamiltonian. And this might be a little bit different from the Hamiltonian that you've seen previously. So let me try to walk you through this Hamiltonian a little bit. So here at the bottom, I have cavities. So this is my first cavity. This is my second cavity. This is my third cavity, and so on. And each of these cavities supports a particular mode, and the frequency is denoted by omega c. And if you look at the Hamiltonian here, that is exactly the piece of the Hamiltonian that accounts for that mode that is supported by the cavity. So what you see is you see the second term here, and that second term just counts the number of photons that we have in a cavity. So for, just to make it specific, the way I'm going to discuss this is I'm going to discuss a system that contains photons. So you might sort of think about there being a photon inside here, or maybe a photon here. And if we do have a photon in there, then we have this particular frequency here. And this is just counting up the energy due to the presence of the photons. But now the other thing is that the cavities are a little bit leaky. So the photons can actually sort of go from one cavity to the next cavity, and they can tunnel from one to the other. And that tunneling is really described here. So what does this term do is this destroys a photon in one cavity and then moves that photon over to the other cavity. And this term here is just to make the Hamiltonian Hermitian. So that's all there is to it. So you can sort of think about this as some sort of kinetic energy term, but in a discrete system. So just think about this as a lattice side 1, lattice side 2, lattice side 3, lattice side 4, and the photons can hop back and forth between these lattice sides. Okay, so that's pretty nice. Now, the next thing that we need, and this is a little bit sort of trickier, is what we do want is we do want photon-photon interactions. So essentially, if you look at this green term in our Hamiltonian here, that is an interaction term. So we have an interaction strength U here. And if I rewrite this using the fact that A and A dagger obey bosonic commutator relationships, then this is basically saying if I don't have a photon on, if I only have one photon on in a given cavity, we don't have this term here, it vanishes. However, say I have two photons in there, then I have a two-body interaction. Now, you should be very critical at this point, because we do know that photons are massless and they usually do not interact. So what I'm introducing here is what's referred to as an effective photon-photon interaction. And this effective photon-photon interaction that I have in my Hamiltonian here is really introduced due to some linearity. So the photons are actually, in reality, there's a medium in there. So in these cavities, there's some sort of background gas, and effectively, that means that the photons are actually interacting. So this is really essentially a photon-photon interaction term here. And that's an effective interaction, not sort of a bare interaction. And this is the Bass Hamiltonian that I'm going to use for my cavity array, just as one example to sort of illustrate what can happen when we're working in a discrete space. Does that setup make sense? Oh, there's a question. Okay, there's one answer. Yes, that makes sense. Can I take this as a general? Yes, everybody is on board. Okay, great. Awesome. So now, before we sort of go ahead and look at the properties of this bath Hamiltonian, or you can call it lattice Hamiltonian, let's actually look at sort of how does this look like in an experiment or in pictorially. So these are images of photonic lattices. So people can actually realize them. This is a 1D photonic lattice. This is a 2D photonic lattice. And, you see it's regularly spaced here. Actually, let me see. It's regularly spaced here. So we have a lattice site here, a lattice site here, a lattice site here, and so on. So before we sort of solve and look at the solutions to the Hamiltonian, I want to ask a question, namely, if we have a lattice spacing of A, so going from this lattice site here to this lattice site here, that spacing is equal to A. What is the condition for the sort of the condition on the size of our two-body bound state, so that we would refer to the two-body bound state as being universal? So say this is my spacing A here. If I want to sort of put a size on my two-body bound state that I'm interested in, how big does it have to be for us to say that the two-body bound state is universal? Any suggestions?
Can I manifest myself, Doerte?
Yeah, sure.
I would say much smaller than A and much larger than A. So I don't know which one is.
Okay, either. Okay, so you got the idea. So how to think about this? A sets the scale, right? This is the spacing between our lattice sites. So if we want something universal, either we're going to be much smaller or much bigger than that scale that I've given you. So those are your two choices. And so in this case, what we want is we really want our bound state to be much, much bigger than the lattice spacing. So in some sense, you can sort of think about this scale A, that's sort of like setting something like an effective range, or the scale of your two-body interaction that we've seen in the case of, say, the previous talks where we had Gaussian interactions with a range, and we always wanted the scattering lengths to be larger than that range. And of course, we do know that the size of our two-body system in the universal regime is essentially given by the scattering lengths. So for something to be universal, maybe we want this to extend over a few lattice sites. Okay, so that's good. And I wrote this down here. So, in my notes, I said, okay, it has to be greater than 10A. Maybe it's only a few sites. So don't worry about the 10 too much, but maybe at least 3 times bigger or so. And in some sense, you can really think about this as the lattice spacing is sort of setting your high energy scale. So using the notation from my previous slide, the lattice spacing A sets an energy scale. So we have h per squared over ma squared. This is some sort of energy. And so, that high energy scale is set by the lattice spacing. Now, of course, there's a little bit of a problem here, and I'll come back to this in a little bit. And that is, for dimensional analysis, I'm putting some mass here, otherwise I don't get an energy. But I also told you, and of course you know this, that the photons don't have a mass. So what mass am I going to use here? it turns out that we actually have a so-called, let me write it down here, we have an effective mass in our system. And so we need to define this to then sort of think about our energy scale here, but I'll get to this. Okay, so let's go back to our setup. And, you know, again, this is just sort of a little bit more detail. I've blown up our cavities here, so you can see this a little bit more. These are actually two mirrors that form a cavity, and then we can have a little bit of leaking out of these cavities here, and that leads to the tunneling. And, you know, just as in our normal case, when we solve the two-body problem, the first thing that we need to do is we need to understand the single body problem. And normally the single particle problem is very simple because our kinetic energy is just p squared over 2m. And so if we have a single particle, it's just a free particle. So we've solved this many times. It's just a plain wave. Now in this case here, our Hamiltonian is a little bit different. But so if we are looking at just single photons, so single excitations, then this term down here disappears. So we don't have photon-photon interactions. And all we have to look at is we have to look at this purple piece of the Hamiltonian. And this is also frequently, I mean, that's just the tight binding Hamiltonian. So we want to look at this tight binding Hamiltonian and look at the single excitation solution. Okay, so let's think about this a little bit. So the first thing is, you know, I already mentioned this earlier, we have this photon number operator. So this thing, I think, did I make a mistake? Yeah, so we are essentially, and I wrote this incorrect, it needs to be corrected, but essentially we have this operator here and that commutes with the Hamiltonian. So this operator here, just let me cross this out, basically just counts the number of excitations in the array. And what turns out to be the case is that operator actually commutes with our Hamiltonian. And so this means that we can diagonalize our Hamiltonian separately for one excitation, two excitations, and so on. So if we go through the calculation, what we find is that the single excitation or the single photon energy is given by this expression. So we have this h bar omega c. That makes some sense because we have one excitation in our Hamiltonian, and we have one excitation that we are describing. And then what we have is we have this minus 2j cosine Ka term here. And it turns out that the single photon wave number is actually a good quantum number. And so essentially what we have is we have an energy band of widths 4j. So if I sort of draw this here, then I can plot my wave number here, and we have the energy, this energy band as a function of k, and the energy band has the widths of 4j. Okay, so this is our energy band. What you can see from my drawing is that this energy band is approximately quadratic near the bottom of the band. So in this regime, we actually see something that looks like p squared over 2m, or my h bar squared k squared over 2m. So this sort of looks like the normal thing. But then as we go toward the what we call band edge here, we do see a different behavior. And so this is the modification of the single particle dispersion that I was pointing out earlier. So it's different from the spin-orbit coupling case that I talked about yesterday. It's a different sort of modification, but it does have certain similarity in that the wave number or the momentum really plays an important role here. Okay, so that's sort of the single excitation case. So one of the things that I do want to look at a little bit is the group velocity. And the group velocity is defined in this way here. So why is the group velocity defined in this way here? So let's look at the sort of normal dispersion again. So let me write down the energy for the case of a free particle, which is h bar squared, k squared over 2m. If I take this and I calculate the inverse of h bar times the derivative of the single particle energy with respect to k, what do I get? I get h bar k over m. Do you agree? Yes, okay. And all I did here is I calculated 1 over h bar dek dk. And if you rewrite this, this is just p over m, and that's of course our velocity. So motivated by this for sort of what I call the normal case, I mean, I'm doing things a little bit hand-wavingly here, but that's okay. So using this, we can similarly just calculate this right-hand side here using this energy dispersion up here that I just gave you. And when we do this, this is our group velocity. So this is quite nice, and we can rewrite this. And I just put it down here again. This is our group velocity. Again, we're looking at a single excitation right now, so we don't have any photon-photon interaction. And so the thing that I want to ask now is how far, you know, what I'm trying to do is I'm sort of trying to give you a feeling for, you know, some of the characteristics of these lattice systems. So what I want to ask now is how far does a single photon travel during a characteristic time scale? And, you know, of course, the first question then is, what is actually the characteristic time of our cavity array? Any suggestion in terms of what would set the characteristic time scale? Remember, I said this term here is sort of like a kinetic energy. So this is our hopping, or this is the tunneling from side to side. So if we have tunneling from side to side, that means movement. So that means that I should be able to take my energy scale divided by h bar, and this should give me the time scale. Okay. So now, then what we can look at is, okay, if we have this dispersion relationship, we can look at, okay, if we have this characteristic time here, then how far does my particle travel? And it turns out during the characteristic time, it sort of travels between not at all to 2a, depending on where I am in my dispersion relationship. So this just gives us sort of a sense for what we have. if we want to look at large times, we need to go to time scales or energy scales that are much larger than J. Okay, so the other question that I want to ask is, what is the effective mass of the photons that are sort of trapped in the cavity array? Any suggestions on that?
So people are thinking. So some suggestion.
Yeah. Actually, I should correct the typo, right? I did forget the, so let me just look at this, right? If I have energy times time, this usually, you know, if you just use the uncertainty relationship or so, this gives you h bar. So if I solve this, I get T is h bar over energy. And now what I'm doing is for energy, I'm using J. So I should be putting to the -1 here. So it's really inverse. Did anybody
Doerte,
notice? Yeah.
Doerte, let me just ask one point about this characteristic time. You have someone already answered, but just to have the intuition, you have h bar omega c. I mean, this also gives some characteristic time if we think about the period of the harmonic oscillator, the inverse of that. Why this is not relevant?
Well, so essentially what that does is it simply shifts your energy scale. And if I look at the physics at the end, it basically sets the zero of my energy scale. So it doesn't actually make a difference.
Okay. So we look to the dispersion relation after all.
Yeah, yeah.
Okay. So there is an answer to you.
Yeah, no, that's right. So that's right. So I think the suggestion in the chat really goes back to sort of, let's think about h bar squared k squared over 2m. So that's again the normal thing that we have. And so if I want to get the mass here, what I have to do is I have to take the derivative twice with respect to k. So, right, I can do that, p squared ek dk squared. That gives me h bar squared over m. And now I want to get a mass. So what I can do is I can divide by 1 over h bar squared. And then if I do that, I put a 1 here, and then I want the mass. So I take to the -1 on both sides. And I think that's exactly what is the suggestion in the chat. I've just written it a little bit differently. So now what we need to do is, for our case, we need to replace the, if you want, normal dispersion curve with the dispersion curve for our lattice. And so if we write this out, this is the expression that we get for the effective mass. And now you look at this and you look at this a little bit more. One thing I didn't say is that J should be positive, but still you look at this a little bit more and you realize that your cosine can take positive and negative values. And this means actually that you can get a negative effective mass. And in particular, you get a negative effective mass when you are sitting at the band edge. So if we redraw our single particle dispersion, and we're sitting at the band. Oh, my drawing is really not great. We're sitting at the band edge at this point here or at this point here. This is where we get a negative effective mass. And so this is sort of a unique phenomenon in the lattice system, and that gives rise to a number of interesting things. Sorry, it's actually, it's not here, it's exactly at the inflection point here. Sorry about that. No, yeah, it's at this point here. So that's exactly where you get very interesting results, because if you now think about F is equal to MA, that is where you sort of get just the opposite response to what you expected. So it's a very unique system. But again, remember, this is an effective mass of the photon. Okay, so let's look at the single excitations with a single emitter. So let's sort of look a little bit ahead, and let's say, okay, I'm gonna take my lattice systems, that's what I just put down here, and I'm now gonna couple my emitter. So it's really just my two-level system as shown here. So this is my two-level system, and I couple that to the array here. And in the notation that I had used, this coupling here is the coupling strength is G. And then in my notation, this here is actually omega E. So that is what I have in this Hamiltonian here. That's my emitter Hamiltonian. That's the coupling between the emitter and the bath. And then this is the bath Hamiltonian that we discussed in some detail, but now with just with a single excitation. So I'm still not considering the effective photon-photon interaction. And it turns out that if you now solve this Hamiltonian here, and you look for eigenstates in the single excitation manifold, you actually do see bound states. These are indicated here schematically in this region, and you can actually see the drawing of a bound state. So this is a emitter that's coupled to the array, and the bound state is basically some sort of superposition of the emitter being in the excited state and the emitter being in the ground state, but dressed with the photons, with the photon excitation. And so this is quite interesting because this is a sort of new or different class of bound states from what we have sort of seen in the FMOF context. All right, so this is what we have in the single emitter case and single excitation. So as I said, what I want to do is I want to go to the regime where our lattice supports two photon bound states. So I do want to allow for this photon-photon interaction. So to treat the two photon excitations, what I'm going to do is first, I'm still going to work in the regime where the photon-photon interaction is 0. But I'm going to look at the situation where I have a first photon and a second photon. And so to start with, I'm really just going to add the energies, the dispersions of our two individual photons, and I get this dispersion relationship here. And what I've done is, just as sort of in the normal case, when we go to the two-particle problem, I've switched to using the relative and the center of mass wave vector. So little q is my relative wave vector and capital K is my center of mass vector of the two photon system. And what we see then is that the dispersion relationship depends parametrically through this term here on the center of mass photon, on the center of mass momentum or wave vector. And this is again very similar to what we saw in the spin orbit coupling case, where the relative energy of the two-body system depended parametrically on the center of mass degree of freedom. And so what does this mean? This means that for each total K, right, remember sort of in terms of momenta, we would have the momentum of a first particle and the momentum of a second particle. And this gives us our center of mass momentum. And so for each sort of total center of mass momentum, our relative momentum can take different values. So I can illustrate this pretty easily by saying, let me look at a center of mass momentum of 0. How can I get this? I can have a P1 in this direction and a P2 in this direction. But alternatively, I can also have a shorter P1 and a shorter P2, or a longer P1 and a larger momentum, but in opposite directions. And what this does is this actually gives rise to this two photon scattering continuum. And I just picked this special point where the total center of mass momentum is 0 and sort of illustrated that we can have a range of values here depending on what we pick for our single particle or single photon momenta. And this is now our scattering continuum here in the two-body sector. And that's equivalent to what we usually have in sort of the normal case, where I would say if this is my energy here, when I say this is my relative energy, then what I would say is that, right, if I'm below 0, this is where I have bound states. And if I'm above 0, this is where our scattering continuum lives. In the case of the lattice, what we see is that we have this band here, the scattering continuum. And this means that our bound state, once we turn on the this U term here, once we allow for this, our bound states could sit anywhere in this regime. And more interesting, maybe also, they could live in the regime above our scattering continuum. So that is pretty neat. Does that make sense so far?
Okay.
Okay, great. So I'm going to go by the one response. Thank you, Claire. And now it's sort of, okay, great. So now we go to, finally, I'm not going to cross out this term anymore. We're actually turning on the photon-photon interaction. When U over J is -1, we get this two photon bound state. Again, I can calculate that two photon bound state for every center of mass momentum. So as I said, the relative Hamiltonian has a parametric dependence on the center of mass momentum. So for each center of mass momentum, I get a two-body bound state, and there's exactly one. And if I make the U over J more negative, then this is where our bound state sits. And again, there exists a bound state for every center of mass momentum. And in terms of the actual equation, this is how it looks like. So my notation here is that I have the total center of mass momentum, and then I call this B for bound state. And this is the expression. And so now we can sort of look at okay, so yeah, let me ask a question first. So in the plot, right, we have this blue state here, this one, and that's for u over j is -1, and we have this red state here, that's for different u, so different effective photon-photon interactions. Which of these states is more strongly bound? The blue one or the red one? The red one is more strongly bound, exactly. So if I take the red state and I indicate the binding energy of the red state, oh, my drawing here is not very good. The binding energy of the red state at this center of mass momentum is this large. At this here, it's this large, and so on. So the binding energy is really measured relative to the bottom of our dispersion relationship. So by comparison, the binding energy of our blue state, and I can hardly draw this, is very small. So it's really tiny, tiny, and it's extremely weakly bound at this point here. So if I draw the little distance, you can hardly see it. So it's quite interesting and unique. And actually,
Doerte,
if we, yeah.
Doerte, no, just to see if you wrote a beautiful formula for the binding energy of the two-body system, but you have the potential there. This is like a contact potential. What you are doing, for me, is not too much clear. You have U over 2, then you have this contact interaction. But this is written in the basis that is not diagonalized your first part of the Hamiltonian. So for me, it's very surprising that comes so simple. Maybe I'm missing some detail.
Yeah. You know, you're absolutely right. This U here, or this term more generally, describes an on-site interaction. And so it's really a contact interaction, right? If we have two photons on one side, then we have that interaction. If they're on different sides, we don't have that interaction. You know, what can I say? It's pretty nice and beautiful. So I guess in physics, if we get something nice and beautiful, we shouldn't complain. But let me turn this around. let me turn this around and sort of say, okay, typically in free space, if we have contact interactions, so our binding energy is h per squared over MAS squared. So I would say this is super simple, right? And so by comparison, this is a little bit more involved, but it's still quite simple, right? I mean, it is true, but it's neat. I mean, it's kind of nice that you know, we can solve some of these problems analytically. And I actually have a reference in a couple of slides that is one reference to what I think is a really nice solution. It's not the first solution to the two-body problem of this type, but it's a beautiful approach. Thank you. Okay.
Actually,
at K is 0, that's the bound state. And okay. So we can just look at this when K is equal K is 0. Okay, so let me just show it this way. So this red state here is bound by this amount at K is 0. And then when we take U to 0, so right, the blue state, this one here, U is much smaller, then the binding becomes smaller. So if I take U to 0, then the bound state really disappears completely. Okay, so let's look at the case that I mentioned previously, where U is positive. And this is, naively you would say, okay, I have a repulsive interaction, so I shouldn't have a bound state. It turns out, however, that you can have these repulsively bound states. In fact, the bound state in terms of structure is just flipped, and you can see this in this relationship here. So these are, as I said earlier, this is where bound states can live. We don't have our continuum states here, and so we can have these repulsively bound states. And so that's something that is pretty unique in lattice systems. But of course, if you're a little bit familiar with sort of metals or semiconductors or things, it might not surprise you so much, because there we always see, say, the first band here, and then we have a second band, and my band structure is really not drawn very well. But we have these different bands, and then we have these gaps, right? These energy gaps. And that's exactly where we can have bound states living when we look at a lattice system. In my case, because I'm working in the tight binding regime, I only have the lowest band. So this one doesn't exist in my setup here. Okay, and just to show you the wave functions, right? Remember, it's a discretized system. So this is one of the references that I mentioned earlier for the state down here, the attractively bound state. The wave functions or examples of the wave functions are given here. This is for different K values. I can actually blow this up a little bit. It's not completely crystal clean. This is for K is 0, so this is at the middle here. This is at K is pi over 2a, and this is at the band edge. And it's actually quite interesting that at the band edge, the wave function is completely localized. And then quite interestingly as well, if we do go to these repulsively bound states, in terms of the sort of, if I think about this as an envelope, I just sort of draw these envelopes here, and I flip these guys around from the bottom. It's exactly the same wave function as we have here. However, the phases are different, and we have this alternating plus minus contribution in our wave function, and that's in all of these cases. So even though in terms of the binding energy, this gap here is exactly the same size as this gap here. So this is the same as this. The binding energies are the same. The wave functions do look a little bit different, and they do have this difference in phase factor, depending on whether the system is attractively bound or repulsively bound. So that's quite interesting as well. Okay, so now let me at least comment. I don't want to show the details. Let me at least comment on the possibility of three-body states. So if we look at that same tight binding Hamiltonian that I discussed, still no emitter, then there exists deeply bound three-body states and weakly bound three-body states. The deeply bound states are sort of like, you have three states and one lattice site. That's sort of the normal thing. And then there are also bound states that are more like sort of a dimer plus a separate photon type state. And if you want to know more about this, I invite you to look at this paper here. And then lastly, on this topic, just to point out, if you actually look at a more complicated lattice structure and you allow for an anisotropy and you go to 3 spatial dimensions, then treating collective excitations, then it was found by Nishida and co-workers that you can actually have the Efimov effect occur in condensed matter systems where your 3 particles are actually magnons. So you're looking at effective excitations in your lattice system. So this universality that was discussed previously by the previous lectures does in fact extend to the lattice system. But the calculations are a bit more involved than what I showed here, so I'm not going to comment on that in more detail. But I don't know if the student who had asked this question is actually in the audience, but this is one possible connection or extension of the Efimov scenario to lattice systems, to condensed matter systems.
Yeah, I think someone asked it, and maybe even mentioned magnons, I think.
Yeah.
I don't remember whom, but I remember seeing that.
Okay, so let me ask, should we take a few minute break and then I continue? How do people feel?
Yeah. Maybe it's good to 30 after the time, no? We have
so we can start 1/2 the hour.
Yeah.
Does that sound good to you, Tobias?
Yes, I think it's good to have a little break now. Okay, Doerte. So please, we continue.
Yeah, that sounds good. Okay, so we're pretty much ready now to sort of look at the situation where we have two emitters or more emitters, and where this Bass Hamiltonian here has non-vanishing non-linearity, right? We discussed this part of the Hamiltonian a bit. We have our emitters, so these are just two-level systems, and then this is the coupling term here, where what we have is we basically have a piece that is bringing us from the excited state of the emitter and then this to the ground state. So we have an excitation that's being destroyed in the two-level system. And in response to that, we have a photon being created. And this is happening at the site where the emitter sits. And then here we have the Hermitian, or the adjunct term, so that our Hamiltonian is Hermitian. So what we want to do now is we want to take advantage of the fact that we can actually adjust the energy difference between the ground and excited state of our emitters. So let's imagine that we're working with a physical system where we can actually adjust this energy difference here. And that's exactly what I drew here. So I'm going to now choose my emitter frequency in such a way that I'm in resonance with the two-photon bound state of my environment. So this thick curvy line, that is the two-photon bound state. So that's what we get just by solving the Bath Hamiltonian. This other line here that's drawn as a thin line, that's the energy of my two-level emitter. And now we're going to turn on this coupling. So I'm going to turn on this coupling constant here so that the emitter, or the two emitters and the two-photon bound state can actually talk to each other. And so what we expect is, we expect that we're going to get some sort of level crossing here. So the sort of states are going to start talking to each other. And then we're going to see if we start the system in both emitters in the excited state, we're going to look at what's the probability of the two emitters to remain in the excited state or to go down. That's sort of what we want to look at. And so what I want to emphasize here is that we are not the only ones and the first ones to look at this. So this is actually, okay, so let me, I got my slides out of order here. So we are not the first ones to look at this. This was looked at by, you can find nice results in this paper by Peter Roberts' group. So what they did is they actually looked at a slightly more complicated case, more complicated than I just described. They started off with not just two emitters in the excited state, but with 4 emitters. So they have this waveguide array, and now they have 4 emitters here, and they are asking, okay, what is the probability as a function of time to remain, or to have all 4 emitters to be in the excited state? And what they saw is that as a function of where they place the emitters, so they place the emitters, say, on site N1, N2, N3, and N4. So it could be this side here, this side here, this side here, and this side here. If that's the case, the spacing here, x is equal to a, or x is equal to 1. And then they change that spacing, and they really see very interesting dynamics depending on the spacing between the emitters. And sort of that's one of the things that we were trying to reproduce and understand a little bit better. And I want to walk you through the calculation a little bit. And I'm going to make this problem a little bit simpler than what was done in the work by Rabel. I'm just going to use 2 emitters to make things a little bit more tractable. And I did want to point out that this is something that has been looked at before. And the other thing that I did want to point out is that if we look at our Hamiltonian here, so right, this is again just rewriting our Hamiltonian here, then this does have quite a bit of similarity with the Dickey model Hamiltonian. So in particular, the 2-level system piece of our Hamiltonian is exactly identical. So this is nice. The other thing you see is that the system Bath coupling in our work or in what I'm discussing here and what was discussed in the famous Dickey model is also very similar. The main thing here is that in the Dickey model, you don't have an array of cavities, but you have one single cavity with a single mode. So that's why we only have the A and A dagger operator. And because we only have a single cavity, the dispersion relationship of just that single cavity or that piece of the Hamiltonian is much simpler as well. And if you're a little bit familiar with the literature, then you really know that the Dickey model that's quite a famous model, and it supports a lot of interesting phenomena. And one of these phenomena is super radiance. So let me just ask, who's heard about super radiance before? Nope. Anybody? Okay, so let me introduce the idea, right? So the idea is that what sort of Dickey looked at is said, okay, let's look at, to start with, a single emitter. And, you know, let's couple that to our cavity, and we have that single mode cavity here. And so if we couple this emitter to the cavity, what's the probability of being in the emitter? And so what you see is, you see sort of, you know, decay. Well, we have a coupling with strength G. So this is our excited state. This is our ground state. So we do expect that there's radiation leaking out of the system. Now, what Dickey then did is put a bunch of additional cavities here, and also the initial state was modified a little bit. But the amazing thing is that because now the emitters are sort of interacting with the cavity in a collective manner, what you have is that there's actually a higher intensity, namely an intensity proportional to the number of emitters squared, as opposed to just an exponential decay, which would be sort of, you know, if you have a single cavity, you have an exponential, if you have a single emitter, you have an exponential decay. if you have many emitters, NE emitters, you would just expect NE decays, right? So it would scale with the number of emitters. But what Dickey found is that there's actually a scaling that goes as NE squared. So it's sort of a collective effect, which means that the radiation out of this level and this level and this level are correlated. And so that's called super radiance. And so this is one of the reasons that makes this topic interesting, because it's sort of a collective effect, and it's caused by non-trivial correlations. And in addition to superradiance, there's also subradiance, which means that actually by adding additional emitters, we can actually have less radiation than you would expect naively. And so, you know, just to sort of come back to these previous results from this work here, what they had found is they had actually found really interesting supercorrelated radiance. And, you know, that supercorrelated radiance, they argued, is actually sort of triggered by the existence of that 2-photon bound state that that is supported by the cavity array. So those are the sort of things that we wanted to understand a little bit more. So to look at this, you know, this was sort of taking a slightly bigger view and sort of saying, okay, but what's in general quite interesting about these emitter systems coupled to cavities or cavity arrays. So now let's go back and look at the equations a little bit more. If we want to understand the dynamics, essentially what we want to do is we want to solve the time-dependent Schrodinger equation. So we're sort of back to, you know, territory that you're familiar with. And one of the things we can do is, if we don't quite know what to do, we can simply expand our unknown wave packet in terms of a set of eigenstates. And in this problem, the eigenstates that we have at our disposal are pretty simple. There's actually another typo in here. This should be excited. So we can, right, I'm working now, and I should emphasize this here, I'm working now in the 2 excitation subspace. So what this means is we can have our 2 emitters be either in the excited state, or we can have the first emitter be in the excited state, but then we do have a photon, or we can have the second emitter be in an excited state, and then we have a photon. Or we can have both emitters in the ground state, but then we can either have a bound state for the photons, or we can have the 2 photons in a scattering state. And this here is really so these states here, this, and this really span our full Hilbert space in the 2 excitation manifold. And now all we do is we sort of put these time-dependent expansion coefficients here, and we recast our problem as opposed to finding this wave function or wave packet here directly. What we do is we write it or rewrite the time-dependent Schrodinger equation in such a way that we have differential equations for all of these coefficients here. So that's sort of how we solve the time-dependent Schrodinger equation. Okay, and so if we do this, what we find And what is well known also in the literature is we can find a regime where, quite interestingly, and maybe to start with somewhat counterintuitively, you can find a regime where the coefficients that sort of describe the situation where we have one photon and one of the emitters in an excited state, that those two coefficients don't change very much. And this really comes from the fact, let me go back, I have to go back quite a ways. This really comes from the it's really nicely and correlated, comes from the fact that what we're doing is we are picking our two-level, we are picking our energy of the two emitters in such a way that we are in resonance with the two photon bound state. We are not in resonance with the single photon band. And because of that, essentially, the single photon states don't actually contribute much to the dynamics, despite the fact that our coupling between the system or the emitter and the bath is actually happening through these single excitations. So, right, the coupling happens through a single of the emitter changing from, say, E to G, and from G to E. So if I sort of sketch this in terms of a physical picture, then we have this sort of situation. And in a very simplified way, we have the emitters in the excited state here, both of them. We have the emitter in the ground state. And when we are here, the two photons can be in a bound state with center of mass momentum K. And then in this intermediate regime, we have an emitter in the excited state and ground state, or in the ground state and the excited state. And here we have a single photon with momentum K. And even though the coupling in our Hamiltonian, and I've rewritten this here, the coupling occurs through these pathways here. Effectively, there's no population that stays for very long in this regime. And effectively, what we can do is we can recast the problem in terms of just these states here with an effective interaction between the two emitters in the excited state and the two emitters in the ground state, with this effective interaction essentially being dressed by these intermediate states. So that's quite a bit, but if you sort of believe the story for a moment, then we can actually recast with these approximations our time-dependent Schrodinger equation in this way. So I have the expansion coefficient for the EE state, and I have the expansion coefficient where my molecule, or where my two emitters are in the ground state, and I have a two photon bound state here. And then what we have is we have an effective interaction between, as I said, this state here and this state, or these states here. And the effective interaction looks, it depends on the distance between the cavities, and it looks very different depending on whether we have a shallow bound state or a deep lying two photon bound state. So does the idea make sense? And for the most part, you don't have to worry about this here. To leading order, we can actually neglect this part. There are situations where this matters, but to leading order, it doesn't matter. Okay. There was a no, this doesn't, okay, so let me see. Does this roughly make sense? So now you get the idea. So we have sort of states that, so let me go back to this picture here. It's a little bit tricky to think about, because if we didn't have these states, we wouldn't have any transitions and population wouldn't flow. But the coupling is such that, so you sort of start here and you have a little bit of population leaking in here, but then that population is sort of leaking down to the lower level. And even though, you know, we need this intermediate state to sort of get down the ladder, we can sort of almost eliminate it and say effectively it's like the radiation can go from here to here directly, but mediated through some effective interaction. So in some ways, we can also think about this as what we're doing is, in some sort of naive picture, we're sort of eliminating the high energy portion of our energy of the Hilbert space. So it's not quite the right picture, but it's an adiabatic elimination. The change of population is so slow here. It's sort of like you just have a leaking through it, and you don't really need the details of what's happening in here.
Doerte?
Yeah.
Doerte, let me just see if I got the physical image. So you have these two intermediate, ground and excited, ground and excited. And you also have the bound state of the two photons. So, I mean, the first impression I had is that the process to form the bound state of the two photons is pretty fast. So the system doesn't want to stay in a place where it is not that you do not have the bound state of the two photons. So it just pass through, no, stop a little bit, and then, I don't know if this is the correct image. I was trying to get this picture in my mind, because you like to form the bound state in some way.
Yeah, so because we are not in resonance with the single photons energy-wise, we can't sort of really decay very much through single photon excitation. So it's a very slow process. It's very far detuned. And of course, the two photon bound state is always there. And so when we are falling into like the two emitters being in the ground state, in the photon sector, we are actually forming, or the radiation goes into the bound two photon pair. So I don't know if that addresses your question, but the two photon bound state as a state is always sort of supported by the stationary Hamiltonian. It's just how strongly is that populated due to the coupling.
So the bound pair do not appear for the other two states, EE and EG. So it's less likely or not? Yeah.
Well, we are working in the two excitation manifold. And so if our initial state is EEGG, so we have the two emitters in the excited state, then because we're working in the two excitation manifold, we don't have any photons in the system. But according to the picture that I drew, right, we have the two emitters in the ground state with a particular K value, and that is sort of energetically in resonance with this initial state. right? Because I drew that 2-photon bound state, and then I said, okay, we choose our 2 emitter energy in such a way that we are in resonance at particular k, I should probably write it this way, plus or minus k values.
Okay.
So this state is
okay.
energetically in resonance, but the point is we don't have a direct coupling between them. Sort of, if you look at our Hamiltonian, if you look at the Hamiltonian again, the Hamiltonian doesn't couple directly to that. So that coupling between these states is sort of mediated or induced by going through states that have, say, one emitter in the excited state, one emitter in the ground state, and then the second photon has momentum k2, or we have the first emitter in the ground state, then the second one in an excited state, and the first photon has k1. So we need these states because that's where our coupling is. But then effectively, we can sort of say we eliminate these states and we introduce an effective interaction between this level and this level, and it also gives us some sort of stark shift.
And this has nothing to do with the systems stays in these EG states, I mean, for little time.
Yeah, it's just sort of, think about the EG and GE states. What they do is they say, give me some radiation and I just pass it on. Give it to me and pass it on. But, it's sort of a flow through sort of, it's an intermediate stage, but it never gets very heavily populated. So it has, maybe 3, 4, 5% in it, but not much more. And, if we do and again, we are not the only ones, if you do the full quantum calculations, you see this sort of a thing. And if you then do the adiabatic elimination, that's shown in black here, you see this sort of curve, and this is the population to be an EE, and this is on a log scale. So, it goes out to very long times. This is for spacing of 0. If we use a spacing that's much larger, you actually see, obviously this scale here, let me switch, this scale here gets longer compared to this. And this is just saying, right, if you have 2 emitters that are far away, and you now have radiation going out of each of them, they sort of need a bit of time to actually see that bound state, which is not quite as big as the separation between the 2 emitters. So you're sort of, here, you're really, your 2 emitters are in the same spot. They can almost directly, quickly talk to that 2-photon bound state. But when the emitters are far away from each other, then the 2-photon bound state is not quite big enough to immediately lead to that talking. So it actually takes a longer time.
Now it's more clear. I mean, it has to do with the positions of those emitters and so on. I didn't got that before. Okay.
Yeah.
Now it's more clear.
Okay, and then we can, so this first calculation here, just to show this is what I just shown you. That was for the weakly bound state. If we go to a more strongly bound state, what you see is that adiabatic elimination. So this red curve here, the full quantum calculation, the red curve, and the black calculation, the adiabatic elimination, don't work quite as well anymore. And that's also well understood, because if your bound state, your 2-photon bound state is smaller, then what that means is that it's more isolated and it's harder to talk to. So we do understand why this is not as good, but it sort of shows you that really you can take the you can take the dispersion And by adding this non-trivial feature to it, namely the two-body bound state, you really can control the radiation dynamics, and you can see interesting correlations that are introduced by few-body physics. So that's really sort of the key point that I wanted to make. The other point that I wanted to make is, that was sort of more toward the beginning, that discrete lattice systems really support universal states. So this is even in the absence of emitters. Then coupling these lattice systems to emitters with a non-trivial mode structure gives another means to sort of manipulate and design particular radiation pattern. And this really opens up opportunities to study dissipative dynamics, and then it also forms the foundation for looking at a master equation formulation. So to finish off, I'd like to thank particular Doerte Blume, who did a lot of work on this as senior graduate student, and also Dave Hill, who is a more junior graduate student, a summer student, Claire Quander, who worked with us on this. And then just point out, you can look at this in the slides. If you're interested in the PhD program, just contact me and we can discuss. And then finally, the last thing I wanna say is I did notice at least 4 or 5 typos in my slides as I was giving the presentation. So I'm gonna fix those and then send Tobias the new slides for posting on the website. So thank you. Thank you for sticking around.
Thank you, Doerte. Maybe people still want to ask some questions to Doerte. It's a good opportunity. Of course, Doerte is always open to answer questions by email, no?
Yeah.
So if someone wants to ask some question, please.
Let me ask one final question. Among the audience members, who actually attended all the long lectures on Monday, Tuesday, Thursday, and Friday?
Kevin,
awesome.
Federico missed yesterday. Martin, Dave.
Awesome, Dave as well, Martin as well. Awesome, great. Thank you so much.
And me.
I really, I do realize that, I would have been awesome, Pierre.
Yeah.
This is great. It would have been so much nicer to, have lunch and dinner and breakfast together in Brazil and hang out and discuss over coffee and
yes.
But
then in the weekend, had some time to visit the beautiful places close to here. I mean, the seaside. It's really a beautiful nature.
Yeah.
Okay, but still, I mean, we are going to make this in Brazil. I think we are going to have other opportunities. Maybe the next one will be in Europe. Then maybe go to US and then maybe back to Brazil. But Doerte, I really want to thank you. I mean, in our name of the organizers, I mean, Jean-Marc, Fimbo, Alejandro, Marcelo, and myself, for really the great job you did. I mean, you open, I mean, this views on the few body physics too much. I mean, this was very nice. It's very wide, not only thinking on a few body quantum particles, either in cold atoms or nuclear physics. You gave really you opened it to us. So we are really grateful for this, that I know was a great effort. to compile all that, organize in such a way is really a lot of time. I know that, and we will have, I mean, all the slides and the movies kept in our site. So I think this is a great material for the students. I mean, really that want to introduce on many of these ideas. I think this will be nice. Now, instead of saying, just look to the book, please go to the classes we have in the critical stability school. So I'm really thankful for the work you have done, Doerte. Thank you.
Yeah, many thanks to Pascal and Alejandro, because I relied a lot on what they already introduced. So I think, and since I am the final person, thank you to everybody who organized that, Tobias, Marcello, Jean-Marc, Alejandro also as an organizer, and I think Hans, right?
Yeah, Hans Fimbo, yes.
Yeah, so thank you to all the organizers. I really appreciate it.
Okay, Marcelo, you are around.
I just would like to thank you very much, Doerte, for your lectures. In your name, I also would like to thank all the other lecturers. I think the lectures were very clear. I missed the half of your lecture yesterday. Unfortunately, I have to make a lot of administration here in my university. So yesterday I missed the last half of your lecture. But thank you very much for your kindness. You always answer our emails very fast. So thank you very much. And okay, I'm sure that all the students here and Tobias, and the other organizers enjoyed a lot your lectures. Thank you very much.
Yeah. And finally, I want to thank, all the participants that make lively, with discussions, even a little bit shy through the chat, but this is really a great experience. And we have to close and ask, and thank to Jandira, to Tiago, and to Umberto, that give all the support. Everything for us as organizers, local organizers, Marcelo and myself, become very easy to do everything and take care of the site. And to our, the director of ICTP-SAIFR in Brazil, that gave all the support, Nathan Berkowitz. So this was, we had all the infrastructure and make our life very easy. So I can only thank you. And for the students, you can access at any time. We are going to upload the revised slides, and so you please assess and recommend to your colleagues. Okay, so thank you very much. Thank you, Doerte. Thank you all, Alejandro, and now Pascal is far away, so maybe Alejandro is around. And so thank you.
Jean-Marc is here also.
Jean-Marc, want to say something, Jean-Marc? Jean-Marc? Okay. Let me see.
Okay, Tobias. Okay.
We have some comments from Eloisa. Okay, I missed it today, first part. I would like to comment that even though having an on-site school is nicer, a good thing about the pandemic online conference and school is that for us, in developing country, yes, this is true. It is easier and more likely to attend. Thank you very much. Thank you, Eloisa, for these nice words. Really. Yeah, this is true. This is our reality. Okay, Marcelo, you want to close? Now we are done.
Just would like to remember that probably the participants will receive an email to make a kind of evaluation of the school.
Yeah.
Some are a few questions just to rate the organization and so on. And I would like to ask you to answer because it's important for the organization of the next school and the events in ICTP-SAIFR here in Brazil. So thank you very much for your participation. Thank you very much for the organizer, lecturers, and also to the ICTP-SAIFR staff and Nathan Berkovitz, the director of ICTP. Okay, thank you very much. Okay. So the school is closed.
Okay, stay safe. Goodbye to you all.
Bye. Bye-bye.
See you the next time. Thank you. Thank you very much.
Bye-bye.
Bye.